So this is the half-life of M&Ms lab, and in this lab we're going to illustrate the relationship between the number of half-lives and the percent activity recorded as a result of how many of the M&Ms, which are representative of isotopes, decay over time. So first we have 200 M&Ms put together in this container, and then I will shake it and then pour out the M&Ms, count how many are M side up and how many are M side down. If it's M side up, that means that it didn't decay, but if it's M side down, that means that isotope decayed and it will be removed from the pile. So I did this a little bit earlier since it would take a while to count all of the M&Ms, and I already recorded the data in my chart. And so then after that, I calculated the percent activity for each of the half-lives and created the graph using the data points. So here is my graph, and as you can see, you have the percent activity on this side and the number of half-lives down here. So we can see that as the half-lives decreased, the percent activity also decreased, and although the points went down in a curved shape, the line of best fit goes straight. And that's because it had a curve because the number became smaller more quickly when you had a larger number of half-lives because it was breaking down into much smaller numbers. However, you can see that it was a sloping process because approximately 50% was lost every time, but that wasn't an exact number, or it would have been a more even line. So then we had some math problems that illustrated the concept of half-lives even further. And my M&Ms were all decayed after 6 half-lives, which you can see on the graph. If it were to continue all the way to 10, it would have been roughly 0.105 over 200 of the original M&Ms would have been not decayed yet. And so then another question was, would isotopes with long or short half-lives be used in medicine? And the answer to that is that short half-lives would be used because radioactive particles are in someone's body for a shorter amount of time if the half-lives are shorter. They are more unstable, but it would be in a person's body for a less amount of time. So then we had calculate the amount of 150 grams of a radioisotope with a half-life of 30 minutes over a period of 2 hours. So that was 4 periods of half-lives that we had to divide by. So that would leave you with about 18.75 grams of the radioisotope. With another problem that you would store something for 10 half-life periods over 30 days, that would result in a total storage period of 300 days. If a school had a radioisotope of 350 grams and kept that from September 1st to June 1st, and it had a half-life of 45 days, there would be approximately 5.5 grams of the original 350 grams left by the time that period of time was over. And so then we wanted to look at the relationship between our percent activity and our half-lives, which are the two things we illustrated on our graph. So we could see that the relationship between these two things were direct because as the percent activity decreased, so did the number of half-lives, or the number of decayed isotopes. So we saw that they were directly related, and we also saw that the M&Ms were a good choice for this activity because just like radioisotopes, which are spontaneous and random, so you don't know if they're going to be decayed or not, M&Ms are the same way. You don't know if when you pour it out, it's going to have M up or M down. And finally, other things you could use for this sort of thing are coins or colored beads or other things that you could differentiate between two sides of the object. So throughout using M&Ms as a representation of radioisotopes, we were able to illustrate the concepts of half-lives and show the relationship between the number of half-lives and the percent activity as the isotopes decayed.